Hi guys, in today's video we'll be learning the Moivre's theorem and the roots of complex numbers. We're going to be going through the basic formulas and basic concept of finding the roots of complex numbers, and in the end we're going to be solving some practice questions. Now let's start off with de Moivre's theorem. Now what is de Moivre's theorem? Now if we have a complex number given by z is equal to r cosine theta plus I sine theta. Now this is a complex number represented in the polar form. Now de Moivre's theorem states that if you raise your complex number to the nth power, your expression will also change in the following manner. So if we raise the complex number z to the nth power, say n, our complex number will be resulting in this form. So the r, which is the modulus of our complex number, will be raised to the power of n as well. And inside, we're going to have cosine n times theta plus I sine n times theta. And this is going to be your new complex number when you raise it to the power of n. Now suppose that we have this question where the question states, find 1 plus I to the power of 6. Now what you can do is, you can expand this, but this is going to take a very, very long time. And we also want our answer to be in polar form if the question asks in polar form. So suppose the question says in polar form. And working in polar form has many benefits to it, as we will later on see in the video. So let's do it in polar form. So first of all, I would want to convert this expression into polar form. Let me call this z. So my z will be 1 plus I. But this is not in polar form, as you see. In polar form, we'll have to make z look like in this form right here. So what is the r here? Your r here is going to be your modulus. And modulus is basically when you sketch your imaginary number on an Argand diagram. Here you have on the y-axis imaginary, and in the x-axis you have the real number. And your number here, your imaginary part is this part, which its coefficient is 1. Hence, it's going to be 1. And it's going to be 1i. And here in your real part, your real number is 1. So it's going to be 1 here. Here, they're all i's. They're all coefficients of i's. So I'm just going to disregard this for a bit. Oops, we got this out of the way. 1 second, I'll have to resketch this real quick. Right here, we got real again, we got imaginary part, and we have here 1, and we have here 1 as well. Now, our point would lie somewhere here, as it's 1, 1. And this line from the origin connecting to our point is called the modulus. It's the r. This is what we're trying to find. So r here is going to be, say, we know this, we can find r through the Pythagoras theorem right over here. It is just going to be, if this side is 1, and if this side is 1, if this side is also 1 of a triangle, it's a right angle triangle, this side will be, let's say r is going to be square root of 1 square plus 1 square, which is just square root of 2. Now, let's go ahead and write this down right over here. So our z is looking something like square root of 2 cosine theta plus I sine theta. But we don't know what's theta, and now let's try to find theta. So theta will be something like this. So theta is actually the argument of our complex number. So as you can see here, the angle that is formed here, this is going to be theta, your argument. And you always measure the angle from the first quadrant. So, for example, if you had your complex numbers somewhere over here, This is just a completely different complex number. Your theta will not be this nor this. Your theta will be, starting from here, it's going to be this right over here. So let's go ahead and find the theta in this situation. Alright, so this is our theta here, and what I can do here is that I can use basic trigonometry to find my angle. Here we know that the adjacent side is 1 and the hypotenuse is a square root of 2. So I can go ahead and say cosine theta is equal to 1 over square root 2. And we know that from trigonometry, this occurs when our theta is 45 degrees, or in other words, it is in pi over 4 radians. So let's go ahead and write this back into our equation. Right, now that we have this right over here, we said that we are trying to find this, z to the power of 6. So let's go ahead and express this. Z to the power of 6 is then going to be your r to the power of 6, so square root of 2 to the power of 6, multiplied by cosine 6 multiplied by our argument, pi over 4, plus I sine 6 multiplied by our argument, pi over 4. And let's go ahead and simplify this. This is going to be 2 to the power of 1 over 2 times, so it's going to be 2 to the power of 3. And this is going to be 8. This is just simple algebra right over here. And here we're going to have cosine 3 pi over 2 plus I sine 3 pi over 2. And this is our complex number raised to the power of 6. Now, of course, if we want to convert this to the basic form, we would simply have to do basic trigonometry again. And so let's go ahead and evaluate this expression. 3 pi over 2 is simply 270 degrees. And in 270 degrees, this expression yields to 0. And this expression right over here yields to minus 1. So sine 3 pi over 2 is going to be minus 1. So this goes back to becoming 0 plus I times minus 1. And evaluating this further, we get minus 8i. So this will be your answer in regular form as well. Both answers, this here and the polar form, exactly are the same thing. Now let's go ahead and find the roots of complex numbers. Now let's discuss the roots of complex numbers. Now let's go ahead and express a complex number that we have, z, which is to the power of some n number. We don't know, but we'll call it n. Now, z to the power of n is going to be equal to, let's say, r cosine theta plus I sine theta. And we didn't raise these to the power of n's because right now we are just calling this some number, z to the power of n, right? We don't know z exactly, but finding the roots of complex numbers, here our aim is to find z alone, not z to the power of n, but rather z. Now, before trying to find the solution of z to the power of n, let's go ahead and take a closer look into the arguments, thetas. The arguments here, thetas, as we explained in the previous section, they're simply the angle that extend from the first quadrant, which is the real section here, right over here, and the imaginary section right over here. And if we have our imaginary number, let's say the point is at here, the angle extending from the first quadrant, the real axis, to the modulus of our complex number is going to be our argument, and it's going to be called theta. Now here, what we can also express theta as, we can express theta as theta equals theta plus 2 pi k. And the reason for this is, if we add 2 pi k right over here, and k is any integer, any positive integer, it can start from 0, it starts from 0, but it is generally positive integers, and it is 0 as well. So k here, it's simply, as we said, positive integers, and if we add, let's say, 2 pi, where k is going to be equal to 1, our angle, let's say we're going to go like this, we're going to go a full rotation, because 2 pi in trigonometry, in radians, is just 360 degrees, where we just take a full rotation and make a circle. And if we go and make a circle, if we measure the angle from the real axis again to the modulus, it's still going to lead to the same theta. It's still going to lead to the same argument. So our argument is essentially staying the same, no matter how many 2 pi k's we add on. And k's can be 1, 2, 3, 4, 5. It's just going to go until n minus 1. From 0, let's say from 0 till n minus 1. Now we're just going to express this, right, the theta here, as theta plus 2 pi k, because it's essentially the same thing. So let's go ahead and write this down. Z to the power of n. Alright, great. Now that we have our complex number in this form, we can go ahead and find an expression for the roots. So as we said, the roots is essentially z here. Not z to the power of n, but z. We're trying to get the z. And so let's go ahead and rise this z, this entire expression, to the power of 1 over n. And do the same to the right hand side, 1 over n. If I go ahead and rise this to the power of 1 over n, from the multiplication rule of the powers, this is going to lead to z. And on the right hand side, what can we do here? Well, simple as that, we can utilize de Moivre's theorem. And de Moivre's theorem suggests that this is going to be risen into the power of 1 over n times cosine, as we said. This is simply, we multiply this entire expression by the power, and the power is 1 over n. So we go ahead and say theta plus 2 pi k over n plus I sine theta plus 2 pi k over n. And let me just, oops, we made a slight mistake. Theta plus 2 pi k. Now obviously you cannot leave your expression as for the roots like this, right? Because this here, we have a k here, and we don't want a k in our expression. That just doesn't make sense for now. So let's go ahead and find the first root. The first root we're going to label it as z0 is going to be r to the power of 1 over n. And remember, in the first root, our k is going to be 0. So if our k is 0, what we're going to do is cosine, it's going to be theta over n plus I sine theta over n. Now, let's say our second root, we called z1, is going to be r1 over n. Now, here k will be 1. We say k is equal to 1. It's going to be cosine theta plus 2 pi over n plus I sine theta plus 2 pi over n. Now let's go ahead and find the last root. The last root is going to be, say, Zn, and it's going to be, k is going to be n minus 1. So we're going to go r1 over n cosine theta plus 2 pi n minus 1 over n plus I sine theta plus 2 pi n minus 1 over n. And this is going to be our last root. Now let's go ahead and work on a simple problem, as this can seem pretty confusing for most of you. And yeah, looks pretty sketchy, but once we work on a problem, you guys can understand it clearly. Now we have a following question. Said z cubed is equal to minus 4 square root 2 plus 4i square root 2. And now we are being told to find the solutions of this expression. Let's go ahead and write this in the polar form. In the polar form, I'm going to get z cubed. Let's go ahead and write the r here, the modulus. The modulus is going to be minus 4 square root 2 squared plus 4 square root 2 squared. And if we express it, and if we further expand this, we're going to get 16 times 2 here, which is going to be 32, plus, again, 16 times 2 is 32, and it's going to be 64, and this is going to be 8. So we have 8 here as our r, and our theta, if we go ahead and sketch this on an arcane diagram, say we have here 4 square root 2, and we have our real part is negative, so it's going to be somewhere here, minus 4 square root 2. And this is going to be our modulus right over here, and this is going to be our theta right over here. Drew it a bit small, but anyways. So what we can do here is that we can find this angle right over here, call it alpha, and then we can subtract it from 180 degrees to find theta. So alpha here is going to be, as this is 8, our modulus is 8, alpha here is going to be, we're going to write cosine alpha is equal to minus 4 square root 2 over 8. And this is minus square root 2 over 2. And alpha here is going to be equal to 45 degrees. Or in otherwise, it's going to be equal to pi over 4 radians. And from this we can find theta. Theta is going to be equal to pi minus pi over 4, which is 4 pi over 4 minus pi over 4 is 3 pi over 4. And so let's go ahead and write down the expression. Alright, now that we've expressed this in the polar form, let's go ahead and find an expression for the solutions. Let's go ahead and find z, to be more specific. To find z, I'm going to raise this entire expression to the power of 1 over 3, and obviously I'm going to use the Moivre's theorem once again, as shown in the previous example. Now, if I expand this, it's going to be z, and this is going to be a to the power of 1 over 3 times cosine 3 pi over 4 plus 2 pi k over 1 over 3 my bad for this, over 3 plus I sine 3 pi over 4 plus 2 pi k over 3. Now, to find z0, let's go ahead and find z0. Our z0 is going to be when k is equal to 0. This is as the same as this following expression, and we know that this yields to 2. So let's get this out of the way. Now, we know that this is a to the power of 1 over 3 is 2, and then if k is 0, we're going to go with cosine 3 pi over 12, because this expression is entirely 0, plus I sine 3 pi over 4 over 12. Again. And now let's go ahead and evaluate this, and this is going to be, if I simplify this, it's going to be pi over 4, and pi over 4 is 45 degrees, and cosine pi over 4 is square root 2 over 2. So this is square root 2 over 2 plus I square root 2 over 2. This is the same thing. Sine pi over 4 is also square root 2 over 2. And if I go ahead and expand this further, I'm going to get square root 2 plus I square root 2. Now this is my first root. First root. Now let's go ahead and find the other 3 roots. So the second root is going to be z1. We're going to label it as z1, and it's going to be the same in a similar fashion. A to the power of 1 over 3, it's 2. Now here it's going to be k is equal to 1. We have to remember, because each time when we find a new root, we increment k, and now k is 1. So it's going to be cosine 3 pi over 4 plus 2 pi over 3 plus I sine 3 pi over 4 plus 2 pi over 3. Now let me go ahead and simplify this, and then we're going to have our second root. I'm not going to evaluate this because this does not lead to a simplified version. You know, without a calculator, we can't really evaluate cosine 11 pi over 12 and sine 11 pi over 12. So I'm going to leave this in the polar form, which is completely fine. And so this means that this right over here, this is also completely fine right over here. Our expression in polar form, this is also the first root. Doesn't matter. From here, I just simplified it to the regular form. But anyways, we can leave it in this form as well. And here we have it, guys. This is our last and third root. This is our third root where k was equal to 2, and we express this in the polar form again, because yet again, expressing this in the regular form without a calculator will be quite impossible, as you can't evaluate these without a calculator, right? So here is our third root, here is our second root, and this is our first root right over here. These two are our first roots. They're just expressed in different forms, right? But in polar forms, this is the first root right over here, this is the second root, and this is the third root. And this is how you find the nth root of complex numbers. Thank you for watching the video. If you have any comments, please make sure to leave it down below. And as well, please make sure to check the description for more updates. And as well as, please make sure to like and subscribe and never miss a video again. Thank you guys. Hope you enjoyed it. Have a great day.